Let's going to discuss about optimization. Now we have a gradient. We know that, well, basically optimization or many methods from optimization, what they require is gradients. And we have already discussed some of them, right? Although I'm just going to present them now with a little name, change in name, right? So what is the idea? You know how basically the gradients are telling you like what is the direction of changes, right? In this case, in your cost function, and you just want to follow this direction or the opposite of the direction, depends on what you want to do, right? So then it's very easy. If we just define a gradient, it could be on the manifold, it could be standard one-dimensional variable, it doesn't really matter. But then with this first approach, which is just a gradient descent, what you do is you take the gradient, you set some step, that's up to you. There's techniques for calculating this, but let's say that, okay, we have a number, and then you just follow the gradient, right? So you have a function here, and then the gradient is telling you, yes, go in this direction. And well, the only thing you do is you do it, right? So you start here, you do this direction like alpha, like this times alpha, and then this is going to be the function, the new optimization function. If you do this enough times, you might get into the local minimum, assuming that it's this one, right? So, okay, maybe yes, it's this one. And this is a very nice technique. It has convergence properties. I mean, it has very strong convergence properties. So if there's a solution, it's going to find it, but it's very slow, right? So the convergence rate is not great. Anyway, we are not using first order methods. For instance, neural nets for training, they use this kind of approach. You just calculate derivatives. You have like some weights that, okay, they are not static, but they change with some heuristics, well, whatever. And then at the end, you're just refining your parameters. There's another family of methods that I think are a little more convenient for us, which are second order methods. And this is basically like, it's called second order because we are using the Hessian, right? So we are, I mean, this will be like for one dimensional, right? So we are just using the Hessian, which is a second order derivative of our function. And then with this information, it's kind of improving what is this step size, right? So we are still using the gradient, but the direction, it's a little weighted with respect to how much it changes, right? So in this case, we'll be here analyzing like, what is this curvature, right? First order is just the kind of linear approximation, but with the second order, it gives you an idea of what is this curvature. Well, not curvature, but let's say, well, yes, let's call it concavity, or I'm sure there's a name, I just forgot it. Okay, so what do we know about this? So we already applied Gauss-Newton, which is a form of second order methods when we were solving least square problems. And how is that? Well, basically, we were approximating the Hessian, if you remember, by this product of adjacency matrix. So this is what we call the information matrix back in the day. But actually, if we take it from the point of view of just doing second derivatives, this is the approximation of the second order derivative, right? So we were already applying like something like this. Here we had a gradient, well, this matrix that we had to invert. And actually, yes, this could also be explained in terms of just draw optimization. So in this case, we were using Gauss-Newton optimization. Just pure second order would be calculating the exact Hessian. And for this, we don't have, on the least square problems, we didn't provide a solution. That is kind of a little more involved. But if the increments are not far away from the optimum, then let's say that this part of the Hessian that depends only on linear part is dominating the others, right? So it's still a very good approximation. This is used many, many places. Okay, let's now discuss about this method. If you have done or if you have get to the last task in problem set 3, you will see that we are commenting about this, right? About Levenberg-Marquardt method. What is this, right? So it's a variant of second order method, but we are simply adding some robustness. So in case that there's a problem for convergence, like, I don't know, you forgot to put like some factors. If that happens, you can still get a solution, but it's gonna be not well defined, right? So in this case, we are gonna have a strange solution. So this, what it's doing is just by setting this lambda parameter, you can control how much the update is, right, on your new parameters. And let's say that, okay, this is just kind of adding robustness to these methods. And this is already implemented for you in MROC, right? So when you solve, you have like 2 ways. I'm going to show it now later. But you have 2 ways of doing this, right? So one is just standard solve, which is doing one step of Gauss-Newton, previously defined here, right? So it's just doing this. And the second one is doing Levenberg-Marquardt, right? So it's checking if the update is actually improving or not, and then, well, regularizes, and then there's like some update on lambdas, but for now, that doesn't really matter much, right? The important thing is this. So there's this regularization term on the diagonal. And this actually helps a lot, right? So when you have a problem that, you know, it's very nonlinear and you need to be careful on how much you update. So this is the default solution with many problems. Okay, let's evaluate these 2 limits, right? If lambda is dominating, you have a very high lambda, then let's say that this goes down, then what you have is almost a diagonal thing, right? And in this case, if you have just a diagonal, well, if you had an identity, this will be equal to the gradient descent. We are only using the gradient information. Well, because the diagonal, it's not exactly diagonal, it's just, I mean, identity, it's more diagonal with different elements on the diagonal terms, but still the idea is the same. It's gonna look similar to gradient descent. The other extreme is if lambda is 0, you just have a pure second order method, right? So you have your Hessian, and this is, well, this is what it is. Okay. Okay. Very quickly, we have discussed a little about updating and differentiation, but then what happens if you want to update your final value? So it's the same problem as before. Summation is not well defined, right? So what is the right way of doing this? Right, so this is only for, well, scalars, vectors, matrices, so on, right? But because we have a group here, we want to make sure that whatever is the new solution, it's going to be in the group, right? So the way of doing this is the following. We just use the same retraction map as before. We do little increments, and then these little increments now are helping us to do the update. And we know that this is going to be in the group as well, right? So this update could be obtained just by this any method, right? So you could be calculating this with gradient descent, Gauss-Newton, Levenberg-Marquardt. And then once you have your solution after, well, whatever differentiation you have done, you have here an update, and you just update it this way, right? So this is for a single pose, but it could be multiple of them, right? And each of them requires this way of updating. Okay, what about random variables, right? So the same could be defined here. I'm just going over and over again with the same problem, right? So before, we were adding noise directly just by summation. This was done for adding noise in the state space, in the action space, in observations. What if now what we have is a function that is a rigid body transformation, right? So we do the same principle. We can define here a mean, and around this mean, we are just drawing samples that are going to perturb it slightly. And because we want all these samples to be in the group, we must use the exponent, right? But the interesting thing is that we could be drawing these samples just from, well, these Lie coordinates, right? So this is just a standard 6x6, and then the transformation we are doing is with the exponent, right? So still you will get samples that are in the group, but we have been, I mean, we can determine like their covariances in this kind of manifold of only 6 coordinates, right? So this is amazing. I'm just here introducing this very briefly, but well, this is another thing that could be used. And actually for us, for state estimation, this is very interesting.